Okay. Acha, so let's then just get started. Yeah. Okay. So today's class actually, will be mostly, I would say, somewhat conceptual because I think the algebra, I guess, you have mostly sorted out. Uh, so where we left last day was basically at. You can see my screen, right?
Yes, sir.
Huh. So basically, we had got the yeah. So we were basically dealing with. So essentially, it was Gaussian beam inside a resonator, or it is also interesting to. It's possible to call this as Gaussian beam modes because it is clear that if you want to have a stable resonator work, that is, if I, this is my resonator, and if I have to have any kind of a wave which is incident on this, then if this needs to be confined inside the resonator, then it is contingent that the beam. So you, even if you come with a plane wave, it is not possible to have plane wave solutions because of the simple fact that a plane wave has infinite extent. You need transverse confinement inside the resonator, which means that the resonator itself allows only beam-like solutions, and the simplest beam-like solution is that of the Gaussian. And we of course attacked it in a different way. We sort of assume that this is like a Gaussian inside, and this is the waste, and we took these as this is R2, these distances from the waste as Z1 and Z2, and we laid down the sort of rule or whatever that the requirement, I should say, that in order for the this thing to be, we know that the stable solution is essentially a standing wave, which means that it cannot change with time. So, and of course, a Gaussian beam is characterized by the Q parameter. So, what we said was that this Q parameter measured at any z has to be the same even after a round trip inside a cavity, inside the cavity, which is basically that it starts, if I start from a particular z and then it goes to one mirror, uh, travels to the other mirror, and then again travels spatially some distance to come back to that same plane, then the Q cannot change, right? That is my requirement for a standing wave. And then we got some stability conditions. I mean, in order to get to the conditions which are required that this be met. So essentially, Q has two things. It has R, it has W, and we one very important requirement, therefore, that this actually this that this QZ remains the same at any Z plane is that the when the beam goes and is incident on any of the mirrors, then the radius of curvature of the beam has to be the same as the mirror. Okay, I have to give that as an as assignment. I have not given it, so I'll give another assignment. This will be a somewhat more intense. I'll give you a week to solve this. So basically, what we said was that the radius of curvature at the two mirrors have to be of the beam. That radius of curvature of the beam at the two mirrors have to be the same as that of the mirrors. That is a big requirement. That gives us one. In fact, those are the two basic conditions. And of course, the I take this as with respect to, this is my origin, the waste. So this is positive, this is negative. So I say that this distance is equal to L. The difference in the sum of this, which basically becomes Z2 minus Z1 equals L. So from those three conditions, we basically get three solutions for Z. I mean, that my constants are basically, as you know, the constants are R1, R2, and L, and we essentially get Z1, Z2, and Z0 square, all in terms of these, right? And what I had asked you, what I left as an assignment, it was critical, that is to find the waist and the waist of the beam, that is the W0, and the beam sizes at the two mirrors, that is W1 and W2. So tell me the answers. Answer bolo. Hmm. Yeah, in terms of G1 and G2. So right, so G1 was 1 minus R1 by L, and G2 is 1 minus R2 by L. And these are of course obtained from our treatment of a resonator in terms of the Ray matrices, and these are also valid for, we can take these parameters for the Gaussian beam as well. So yeah, so that was the exercise. So kya hai? Tell me.
So
Nice form.
W0 is
Yeah, that is a
lambda
big one.
L over pi whole square root.
Yeah.
Then G1 into G2 uh,
Mm.
into 1 minus G1 G2 divided by G1 plus G2 minus 2 G1 G2 whole square.
Nice. And this
And
whole
then
thing,
and this whole thing 1 by 4.
correct. W1.
W1
Let me write
W1
it
is
again.
lambda
Wait,
L
wait,
over
wait, wait, no.
sure
Them too close. W1. Bolo. Yes, same, right?
yes sir, lambda L by pi square root,
Mm.
and then G2 divided by G1 into 1 minus G1 G2 whole to the power 1 by 4.
W2 is basically just this, and then
Then
instead of
just replace
G1, you have
G1
G2,
with
right?
G2.
Good. So, guys, I hope you derived this, right? This is some, I think, useful algebra that one needs to do. So, acha, why did I make you? So, from what do we kind of infer from here? So, very clearly, what you see is that we define, so this tells us, so that these are the spot sizes at mirror. If I say that this is M1 and this is M2, right? So this is the spot size at M1, this is the spot size at M2. Okay, so what we basically have to have, we sort of insist, is that, so if I say if let the mirror diameters, uh, a radius, no, I should not say diameter, mirror radius, say one of the radius, whatever, say this is the mirror radius of either M1 or M2, whichever, be something, let a mirror radius be A, not the, let a mirror radius be A, be something like A. Okay, so it is completely contingent, if I want to make life simple, that the waist size has to be smaller than the radius. That is a must, because if you do not have that, then if you basically have something like, this is the beam and that is my mirror, then you're going to have all kinds of strange things. You're basically going to, if this is my mirror and this is my beam, sorry, let me write this properly. If I say that this is my mirror and this is your beam, then you're going to have crazy things, because these at the edges, you're essentially going to have a lot of diffractions. And this is going to be very, very complicated. So for the cavity to so that our whole, the premise, or the way we have built this up, in order that sort of remains, that can be applied, it is absolutely crucial that A has to be much, much greater than W1 or W2. It has to be greater, depending on which one I take as A. It has to be that, right? So this trait imposes a certain condition, which is that. Acha, so one thing that you can clearly see is that, so what is the maximum, so what is the order of this term? So both of them are the same. I mean, both the W1 and W2 are the have, so this is a constant in both, and this is also, so essentially what we have is something like, it has to be some W, let us just write this in a different way. So we can write this as something like root of lambda L by pi into some f of G1, G2, right? So what do you think is what is this order, this order of this function? What is the typical order of this function? Huh? This thing, basically this thing or this thing. It's typically of the order of what? Generally it should be of what level? What? Hmm? What do you think?
mm, few mm,
Huh? Sorry?
few mm.
Hey, come on, Rohan, this is dimensionless, yeah. What are you saying? G1 and G2 are
Oh,
dimensionless.
I thought you were asking W.
No. अरे क्या लिखा देखो. I wrote this part. This is a constant. Na? This part I wrote as function of G1, G2. Na? So this will be order of what? What will be this thing as an order of? And this is like what? I mean, what do you think this will be?
What is the order of L?
But no, I'm saying order of this guy. This term, this G1, G2 by G1 minus G1, G2 and G1 by this thing. This is the value of this will be of what order? I mean, see, remember again that G1, G2 typically cannot be more than 1. I mean, they are positive and they are like between 0 to 1, right? So then obviously these two will also be of that level because you're multiplying and dividing these things. So essentially these two will also be, if you know that these are that, then this also should be of that level, in the sense these should be of the order of unity. And that, yeah, so that actually we can also sort of insist that this is going to be the case from the simple thing, requirement that, actually let us do that first before I jump into this. So we need that W0 needs to be positive, right? Clearly, right? So in that case, then obviously this has to be non-negative, right? This G1, G2, 1 minus G1, G2 cannot be negative, right? So very clearly, this implies that your G1, G2 into 1 minus G1, G2 will be between these, right? है ना? Because this is quite clear, because you cannot have them this thing. I mean, so that these are this thing. I mean, positive. They cannot be sort of less than 0 for sure, and so actually I should not write this. This is not correct. So I should basically write that this part should not. It's a 0 less than 1. I should not write. That is wrong. Basically, I should just write that. Sorry, this is not correct. So essentially, this is not correct. So this cannot be less than, this cannot be less than 0, right? So basically, you can say that G1, G2, 1 minus G1, G2 has to be greater or equal 0, right? Otherwise, this becomes, so what is crucial is, if this is not 0, if this is negative or something, we actually infer that a beam-like solution inside a cavity cannot happen. This is a very interesting, important thing that follows. Unless this is positive, you cannot have a beam-like solution inside the cavity, because any beam-like solution requires that you have to have this a waste to be non-zero. It cannot be negative, right? Can you hear me, guys? By the way, my internet is very bad today.
Sir,
Yes, yes.
whatever you wrote previously, that
That is
G1,
not correct.
G2
That
into
is not
1
correct.
minus
I
G1,
cannot
G2.
put that one. I
Sir,
cannot
no,
put
sir,
that.
even that is fine. I mean, what's the problem there? If
Now
G1,
I'm
G2
saying
lies
that
between
no, but
0 to 1.
Hitesh, my logic should be like this, right? I should not directly claim that it is between 0 and 1. How can I claim that?
Because the
This is
G1,
fine.
G2 lies between 0 to 1. So G1,
I know, yeah,
G2
but
1 minus G1,
le-
G2 has to be
see, it will come to
between.
that. It will straight come to that. I mean, this means that this part is between 0 and 1, right?
Yes,
But
the
straight means, right? But I think what I felt after writing that is that it is not a. I mean, we know that from our understanding in ray matrix, we know that it cannot be that thing. But from this equation, I cannot write that. And from if I forget about, I say I don't know what G1 and G2 should be. Suppose I don't know, right? Then from here I cannot write that. So see, guys, what I'm trying to do is actually something, I mean, different. We are trying to see. Remember, we had started with a assuming that there is a Gaussian inside, and we were saying that if the Gaussian remains invariant, what should I require? So see the fun of it. By doing that, now I have come to a point where I actually say that if you have to have this cavity working at all, you need this thing to be non-zero. And if you have this to be, I mean, sorry, positive, very sorry, positive. If you want this to be positive, acha, let me just rub this out. So if W0 is not positive, is not positive, we cannot have beam like solutions inside the resonator, which is very, very important. So it is like, see what we are trying to say. See, so this you agree with, right? If this is not, if this becomes negative, there is no Gaussian beam. That is over, right? You cannot have a Gaussian beam because the waste negative matlab it is unphysical. It doesn't make any sense, right? So, but then if I insist that, if I insist that, if I insist that this has to be greater than 0, so directly this says that your 1 minus G1 G2 has to be greater or equal 0. So clearly this says that this, and this is exactly what we had for your this thing, which exactly what we had for our this thing, what is that, our plane, ray, when we treated the ray, the we approached the problem using our ray picture with the ABCD ray matrices. This is exactly what we got. Ah, this is exactly what we got. So this is very beautiful, right? Because see, you have started with the picture of a beam. Okay, we have not said anything about railway, nothing. We started with a beam like, more. We said that there is a Gaussian beam inside, and then by arguments of physics, we said that if you wanted to have stable solutions, then the Gaussian beam cannot change with time. And if I go along with using that, I essentially go to the point that I require the same kind of condition, the exactly same condition for resonator stability that we had. So let me just write down that this is exactly the same condition for resonator stability that we had in the ray matrix picture. Exactly this. But there is actually a big difference. There is actually a big difference. Can you? So see, in this is really nice. So think, see in that picture. So this is all. This is mathematically this is valid. But if you actually have G1, let me just go to a new slide. It's getting very okay. No, it's actually it's better to let me just make this shorter. So see what we can actually see from there in that picture we did not have any issues about, see, remember what the G1 G2 were for a plane mirror was, it was 1, right? It was not a problem, it was exactly 1. And there were also situations, I think, for that plane and concave and convex we had, I think, 0 or something, right? Something like that, which were both allowed. Now however, can you tell me, let me write this, are G1 G2 equal to 1 or 0, that is basically either of them is 1 or 0, are problematic? Let me ask this. Yes, are these problematic?
So equal to 1 is
Answer this.
problematic because waste becomes
Yes,
infinite.
exactly. This is at 0.
At 0, the waste has denominator 0, so it becomes infinite.
Now waste, no, which waste?
The W1 or W2, anyone.
Exactly. So they are both problematic because they are telling you that if so G1 or G2, should not say divided, we should think is divided. If G1 or G2 equal to 1, right? Or yeah.
Or even
Yeah,
0.
no, but it's basically, yeah, no, no, see, G1, G2, I should write G1, G2, 1. If G1, G2 equal to 1, this calamitous, which means, so G1, G2 equal to 1 essentially means that both have to be 1, right? Yeah, okay, that is fine. Yeah, so essentially I can write G1 or G2 being 1. That is fine, right? But no, but can we say that if either of G1 or G2 are 1, there is a problem? Can we say that? Because if G1 is 1, I think G2 can be different from 1, no? So that is not correct, probably, right?
So both have to be
Yes,
1.
sir, because
So
no,
that I cannot write. That I cannot write. So basically, if G1 and G2 are 1, basically both W1 and W2 infinity. Also, this is interesting, if G1 or G2 is 0, either W1 or W2 is 0. This is, I think, fine as a statement. So this is exactly what we have for a plane mirror, and that tells you that a plane mirror actually is a very problematic resonator. See, this
Sir, you are not audible if you can hear us.
Oh God. Hello. I was kicked out. Hello.
Yes, sir. We can hear you.
Yeah. So I don't know till what point you heard me. So I was basically saying that this Fabry-Peri experiment in your second year, who had done? Shubhranshu, I know had done. Shubhranshu around?
Yes, sir.
So you remember you had done it, right, Shubhranshu? Because we were over with experiments, and then you had to suddenly do that experiment, right?
Yes, sir.
So remember there actually. Oh, but that also we had concave mirrors, I think. No, we didn't have plane mirrors. Oh, there also. I think we
I
had. Remember, did we have plane mirrors?
I think so. Plane mirrors, but
No, but you had. Yeah, I think you had plane mirror. I don't remember actually. That cavity is, but see, that's what I'm saying. So it is not that it doesn't work. Okay. So I have generally used plane mirror cavities and all, but the problem is they are extremely unstable, very unstable. So what happens is, if you have any slight perturbation, then basically the cavity drifts all the time. The frequency goes all over the place. If you look, if you see the cavity fringes, if you say scan the laser, if you get fringes like that, and they will just keep on drifting. So they will go like this continuously all the time. So the cavity, it's a very unstable cavity, that is for sure. Okay. But this actually tells you that these extreme cavities are problematic. So therefore, combinations of spherical and plane mirror, or both spherical mirrors, are what you need. Okay. So therefore, this tells you that combination of
Sir, in case of plane mirrors, I mean,
uh,
can't we like use a box which like both the top and bottom part is also covered with a mirror? So in that way, the beam
hey,
won't
but it will
go out.
not. No, but Hitesh, the problem is that it will go all over the place, right? Because it will just hit the top, and that ray will bounce off somewhere else, and you have a complete mess. No, you're saying that I catch the ray and put it back, but you will not get it in the. And it will not flow back and forth. Nah, if you have a reflector here, it will go crazy, right? I mean, you will not get it on top of each other. But you will not lose the light, but getting it back into circulation is one hell of a problem. Okay,
So we
so
can't see the screen.
actually, you can't see the screen. Oh shit! I forgot to share. Sorry. I forgot that I had been thrown out. Sorry. Oh, okay, sorry. Yeah, so I was writing combination of plane and spherical mirrors are most effective, are most stable, are most stable. Okay, so this is very beautifully apparent now. Now let us just start this. Now let us go at this. Go to this another very crucial thing. That is, as I had told you last class, that here actually, see in the ray matrix, the stability thing that we had done there. Acha, oh no, let me finish. I forgot that other one, that Fresnel. So basically, let us again write this Gaussian resonator modes. Modes continued. Yeah. So we wrote down the thing of that. So A is the mirror radius. Then we basically wrote that. Acha, so now it is. So yeah, we wrote that A is equal to some lambda L by pi f of G1 G2 f of G1 G2, and now you will agree that this will be between 0 to 1, right? Between This is going to lie between 0 to 1, because that is what we have seen right now. So that sorry, much greater. So basically that this is implying that, so if I forget about pi, so I basically need that this has to be valid, right?
Sir, the
So this,
denominator part of f G1 G2 will be between 0 to 1. But then in the
yeah, but then
numerator
you
we
have
have
that
G1
either
as well.
G1 or G2, na?
But
Yeah,
sir,
but
that
if you
that can also
uh,
be between 0 to 1. So I mean the uh, the division won't converge between 0 to 1.
I
If
mean,
the
it's on the
numerator
order
is
of unity, in the sense that, see, you, if you think of that, if you generally choose combinations, so remember that you basically I think you can. I don't know if you can write this as some G2. If you just think of combinations, then it's probably not correct to write this between 0 to 1, but it's in the order of 1 actually, and it's not going to blow up because if you have one of them very small, then I mean, see, remember, it is like it is basically G1 G2 divide by it is again this G1 G1 or G2 1 minus G1 G2, right? So just think of
Yes,
it.
sir.
If it, and you know that these have to be between 0 to 1. G1 or G2 have to be 0 to 1. So
Yes,
if
sir.
now obviously if one is no, so obviously I'm not, the 0 and 1 are not being in, I mean, we're not saying that for the cases when G1 G2 is equal to 1. So that
No, sir.
basically is an unstable cavity that
No,
is
even
gone. I mean, we're
in
not thinking
general
about that.
case.
But if you think of the other possible combinations,
Sir, you're not audible again.
thrown out again. Can you hear me?
Yes, sir.
Yeah, I got thrown out. The network is terrible today, absolutely here. Yeah, so what I was saying was that if you know that G1 and G2 both lie between 0 and 1, I mean, if you do, just run a simulation or something, I think it will find out that this quantity will not increase too much because any of them increase, then the other will probably bring it down. I mean, I don't know. If you just think of it, this is basically, it is of the order of like G1 by G2 or G2 by G1, and then there is it is and there is a G1 G2, right? Both of these are there. So basically, both of them compensate each other. I think that's what you will find. So, Acha, oh shit, I'm not sharing my screen, no? Oh man,
Yes, sir, you're not.
I'm sharing it's throwing me out every time. Oh, today is going to be a very bad day. Anyway,
Sir, also, like
what I was saying
either
basically
G1
was,
or G2 being 0 means that
hmm,
if we look at its formula in terms of L and R, it's 1 minus L by
uh,
R. So if G is
hmm,
0, it means
hmm,
this L equals to R. So
hmm,
for
hmm,
some reason, we cannot allow to have such a configuration. I mean, why is it? So it's like it's weird.
so L equal to R, man, if you think, generally your focal length, so it's a hemi thing, right? So basically your focal length is typically 2R, na? And R is 2F, right? So if so L equal to R means that your focal length is yeah, so it is basically, so that this two wait a R equal to 2F, right? Or which one? The for the radius of curvature
Yes,
and,
sir.
2F, right?
Yes, sir.
No, I think R 2R equals F. Yeah, 2R equals F, or is R equal to F? 1 second. Radius of curvature uska kya hai? I forgot. radius of curvature and focal
R
length.
equal to 12, sir.
R equal to 2f, right?
Yes.
Yes, sir.
Radius of, let
Sir,
me just
from
check
length
one.
maker's formula, if you put R1 equals to 1.
Yeah, okay. Let me just check once. Surely.
Yeah, so you'll get 2 by R equals to F, so which is R equals to 2F.
So R equal to 2f, R equal to 2f, right? So R equal to 2f. Yeah, so basically you're saying that if I have two things like this, if I have, so then the spacing is 2f, right?
Yes, sir.
Right, the spacing is 2f. This thing is 2f, right? So anyway, this thing is probably called a hemiconfocal or something. 1 minute. I think this was called when L equal to R. Remember, let me just figure out this. L equal to R is probably a equal to R. No, it's actually a confocal.
Oh, that is fine. My
No, but
question is,
actually a confocal is actually quite stable generally. So I'm just wondering. So, oh, okay. G1, G2, 0 is not a problem. See. Oh, yeah. Hey, what a stupid thing. No, but G1, G2 means either one of them is 0, right?
yes, sir. I'm saying you can take any one to be 0.
So this is actually strange because generally a confocal resonator is supposed to be a pretty stable resonator. Why do they have this problem? I mean, generally G1, G2 equal to 0. I mean, yeah, that basically means that one of them is 0. So, uh, it's basically called a marginal this thing, but yeah, it's actually a bit strange because typically when you have f equal to 2 odd, that is supposed to be a pretty stable resonator. So I have to check this why this is not considered stable in the sense that, see, if a confocal resonator essentially is something where if you have the image here, the thing just goes like that. It is essentially something like this. But that is typically supposed to be quite stable. So both being, yeah, it's actually a problematic thing. So if I'm saying that if any of them is 0, yeah, so then G1, G2 basically means, yeah, this I have to look at this. Basically, I don't have a direct answer for this at the moment because I have a feeling that, see, if G1, G2 is 0, then yeah, I mean, our condition is fulfilled, but this is typically not a very, I mean, see, but at the same time, a confocal resonator is supposed to be a quite a stable resonator. So why are they? See, one is a problem you can say because the spot kind of blows off. But why is it that, I mean, G1 equal to 1 you can appreciate is a problem, right? Because that
Yes, sir.
basically means the infinity, it goes to infinity. But 0 should actually not be a problem because that essentially means that my thing is not did not blow up so badly. Let me see. I have to probably check this a bit because somehow people,
We can continue with the class.
yeah, we can probably continue because this is actually a problem. I completely agree that confocal resonators are supposed to be quite stable. So I don't know why that is supposed to be a problem. People don't really talk about this so much. Anyway, so let us. Acha, so what I was saying was, in general, this is if I say that this is of the order of that level of, not of the order of unity, then I will require that this quantity has to be much this a square must be larger than lambda l, or that this thing has to be much greater than 1. So this is essentially the thing called the Fresnel number, okay, for any cavity. Okay, and you can also figure out that, for example, you can just quickly solve and tell me. So if you have, say, lambda is like whatever 600 nanometer, and say your L is, say, a stable cavity, maybe whatever 50 centimeter. Okay, so tell you, see what L comes to be. So 50 centimeter, 0.5 meter. So see what your A squared should be typically. Just tell me the number and let me see if I can think of what happens. So this is 0. Just tell me once quickly.
Is it 0.5 meter, right?
Yeah. Typically, that is the thing.
Yeah, so this is 300 nanometers squared.
Huh? Yeah. What is the diameter required of the mirror?
Diameter. Okay. 0.55 millimeter.
Continuously getting thrown out. Yeah. What is the answer?
0.55 millimeter.
Yeah. Why, millimeter? That's small.
Yes, sir.
Huh? Are you sure? All of you getting the same answer?
So that is
Millimeter.
600 nanometer, and that is 0.5 meter.
Yeah.
Yeah, so
So it has
point.
to be root of that, no?
No, sir.
0.5 meter. So
Sir,
millimeter आ रहा है
it
या
will be
centimeter आ रहा है?
it will be square root of 300 nanometer.
हाँ, nanometer का square root तुमको centimeter. Yeah, so it will be, think of this. No, हाँ, so right. So 3 to the power minus 7, right? तो millimeter कैसे आएगा?
Yeah,
Is
because
it coming to millimeter? हाँ,
yes,
you're right. You're right. Yes. Exactly. So basically, A has to be greater than कितना बोला? 0.5 millimeter, right?
0.55.
So fine. So then you need basically a one, something like so typically, the mirror sizes are typically of the order of, say, that is why we have, like, at least something like half-inch mirrors. This is a typical size that we have. Typically half-inch mirrors you have that, because you need to have this much more. So half-inch means 12 type, 12.7 Okay. Acha. So now let us just this confocal thing I have to really, because nobody really talks of it so much, but let me just think of this a bit more. Anyway, so yeah, as I was yeah. So now what we just quickly do is look at your yeah. So we look at the phase thing. So we know that standing wave pattern wave pattern needs to be established inside a resonator, right? So now just tell me, okay, you remember the spherical wave formula, right? So you had now be the Gaussian spherical wave was, it was written as what? So we had some amplitude and some whatever. So I think we had a z0 by z, no, yeah, it was, I think 1 by z, yeah, so it has to be z0 by z, some z0 by z. Then we had e to the I k z, e to the minus I phi, and then e to the I k some x square plus y square by 2r z, and then this e to the minus your x square plus y square divided by 2 omega square z we had, no? Acha. So now just tell me, when you so what will be the phase change when you actually go when you finish one round trip? So what will be the phase change? The phase, the basically the yeah, so the phase change will be what? So if I say that this phase of theta z, if I say, what is that phase? Huh? What? हेलो, क्या होगा? फेस चेंज कितना होगा? हेलो,
Sir,
am I there?
yes,
हाँ,
sir. Oh,
it will be what?
it will be 2 pi by lambda into 2L.
No. In terms of this thing of the wave, yeah, obviously that is fine. I mean, it is, so basically the phase difference has to be some integral multiple of 2 pi. That is for
Yes,
sure. But from here, what is the phase that the beam sort of acquires? What is the phase in the, yeah, in the z direction? What is the phase? This in the z direction, my phase is, that is, so you will be, so after round trip, you know that the phase will be
We can't hear you again.
so this is just kz minus 10. Oh god,
And now
hello,
we can hear you.
again I was out, no? Arey, this
Yes,
is
sir.
not working, man.
yes,
It's
we
just too
couldn't hear
bad.
anything.
Shit, man. Okay, we are still presenting. Okay, so somehow I was thrown out, yet I was presenting. So you can see the screen.
Yes, sir.
Yes, but we
Anyway,
couldn't
so I
hear
can,
any
yeah,
part of
so basically what I was saying, so okay, so this, let us just go through quickly. So phase is basically this in the z, right? The phase change is basically kz minus phi, na? So this is nothing but k tan inverse z by z naught, no? Phi was tan inverse z by z naught, right? And
Yes,
How
sir.
after,
do we know
huh, what?
this? Tan inverse
What?
z by z naught? How do we know
Hey,
this?
phi भूल गया, that is what we had derived. तब derive किया था ना, उसमें derive किया था Gaussian में. Phi
Okay,
value is
let
tan inverse z by, वो देख ले notes. We had derived this. So this is basically 2 pi, right? So now you can say that if I go from, so this implies that if I go from, say, from z2 to z1, theta z2 to theta z1, I will basically go from, achha, this one I will not hide actually, because this is telling me whether I am there or not. Which is very important. I'm not going to hide this, because yeah, if it goes off, I know that is, yeah. So basically, this is nothing but k of z2 minus z1 minus tan inverse z2 by z0 minus tan inverse z1 by z0, right? So basically from here, so now this has to be sort of simplified. Okay, this has to be sort of simplified. So so then this is acha. So you know that if this is, remember, this is just one trip. So round trip is 2 pi. So for a single trip, so for this is the total phase. So phase change for Z2 minus Z1. This is like just one trip, right? So it's Z2 plus Z1, not 2Z2.
Sir,
Z2 plus
this round trip is some integral multiple
pi's.
of 2 pi, right?
Yes. It is 2n pi, right? So
That
this
is
is, I'm
because
not
we
doing
are
round trip.
that is because we are looking at standing wave. Is it?
I had to, obviously, this is a constructive interference, right?
Okay.
This is essentially a constructive interference, right? So phase change for Z2 minus Z1 is essentially this, right? And that will be equal to some n pi, right? Because I am taking half of the round trip. A round trip matlab twice hoga, half of the right trip, right? So basically now, if you actually solve for this, abhi ye thoda algebra hai, okay? So if you just solve for this, then you will, this again I will, we cannot solve, I will not solve here. We will basically solve this, I will again leave this as an assignment. So what you will uh, essentially get is that yeah, so something called the, the allowed mode frequencies or something that you will get if you actually solve for this. So remembering that, if we define, so we define this mode frequency, which is basically some kc by 2 pi. Okay, then you will basically get, so if I call this some new m, then what I will get is this, from here, if I say, if you just get this, then if I just do this, then you will essentially get this new m to be equal to some, this again I will just, you have to derive this. So why is this mode frequency? So this mode frequency essentially means that the period of the standing wave. Okay, so that means if I were, so that that the stability condition is basically given by 2d equal to some n times lambda, right? So if I were to write in terms of frequency, this is the frequency that will come. I mean, some kind of mode frequency we define like this. So if I define like this, then I will essentially get something like c by 12 m plus 1 by pi cos inverse root of g1 g2. Okay, so this is basically telling you this, what is the meaning of this mode frequency is, if I were to say I was changing my input wavelength, if I change my lambda and I was looking at the intensity outside the cavity, I will get something like this, right? So this is basically some mth mode. This is by m plus 1th mode. This is by m plus 2 mode, like that. The mode frequency essentially is the frequency of these. So basically this difference. If I should not say this, I should say this as nu. Okay, so this is essentially telling you ki how much frequency I need to change of my input in order to go to the next cavity mode. You understand? So you know that this is there, na? So this is there. So I know that I need to, if I want to go to the next mode, that if I go to n plus 1, I need to change lambda.
Sir, we can't hear you.
Oh, again I was thrown out. I don't know how much have you heard.
Sir, when
Yeah.
you changed n to n plus 1 and then you were making
Okay,
change to lambda.
okay, sorry. I can't even understand where it is going. It is absolutely horrible today. Anyway, so what I was saying was that this frequency essentially means that if I have, if I just write these terms in terms of frequency, lambda just c by nu, if I just write in terms of that instead of lambda, then I will essentially, this means, so did you hear this part, that if I change the
Yes.
frequency of my input, then I can go from one mode to the next. So this frequency essentially means the difference between the m and the m plus 1th mode. Okay, and it will basically, if I solve for use this kind of a phase condition, this is my phase difference, and if I write this thing down properly, then I will essentially get something like, if I define this as the mode frequency, then I will get this expression, and if I put g1 g2 equal to 1, then my new this, so basically that is the for the this thing, your plane mirror, right? So you get nu m is cm by 12, and of course if m equal to 1, so m equal to 1 mane, so the difference, so I should not say m equal to 1. If I say that, if I want to find out the gap between the difference between nu m and nu m plus 1, that is essentially c by 12, and this is called the free spectral range of the cavity. This
So
is
I have a
essentially
question.
called the, well, let me write this, free spectral range of the resonator, FSR. हाँ, बोलो.
Sir, I'm getting
बोलो.
confused between two kinds of frequency. One is
Hmm.
the frequency of the inherent frequency of the
Input.
light, that is
Yes,
nu
that is very
lambda equals
different. That has
and
nothing to do with this. This is basically the so it is, think of this, so essentially, it is, if you have your string, right, if you have a stretch string, right, this is your thing like this, right, so then this is one mode, then these are the other modes, right. So this is what we have here, is the difference between these individual modes. This has nothing to do with the input frequency, but it tells you, depending on the input frequency, I mean, sorry, depending on the length of the cavity, okay, you will basically get, so
Did sir get disconnected again?
are really, yaar, I'm just going crazy. Horrible. What, when did you, how much did you hear? Hello.
sir, almost nothing.
Oh, nothing. Hey, chodo yaar. Shall we meet tomorrow once? This is just too bad. This is just horrible. Every second I'm getting to pause. Chodo, it's not going to work today. I mean, every 2 seconds, if it goes, then I cannot really teach like this. Chodo, we'll do a class tomorrow, okay? 5 o'clock. I
Okay.
will, yeah, this is a very important part. I don't want to keep on getting destroyed. I mean, I will go to Izer, so maybe Izer also, if this is like this, I don't know. So Chodo, we'll continue tomorrow. Let us just take it from there tomorrow, because it's just disturbing too much today. Okay, so just tomorrow we will try again. 5 o'clock. Okay, guys. Then tomorrow we meet at 5. Did not want to take a class tomorrow, but I can't help it. Impossible. I will take a class tomorrow.
Okay, sir.
Okay, this is just too bad. This is every 5 minutes. If it goes like this, I can't take. Tomorrow 5 o'clock.